likely to have larger thermal conductivity, right? So that's what I want you to extract out, okay, from these 4 points. Okay, so is that, so you get what the kind of questions that I might ask you? Okay, so okay, so the other thing that you should know is when you heat up something, it expands, right? And that's called the thermal coefficient of thermal expansion, right? That expansion induces some strain in the system, right? And that's the change in length over the original length. And so the strain that is induced is directly proportional to the coefficient of thermal expansion, right? And the change in length is directly correlated to the differences in temperature. This equation is in the review slide, the first slide. Okay, so you need to know this equation. Okay, and so when doing the exam, please don't ask me what equation to use for this question, because you should just know this equation. Yeah.
Why is it flipped to negative strain instead of positive strain?
One is tensile and one is compressive. Tensile means longer, right? Compressive means, so when does compressive stress take effect? If you go down below room temperature, you could actually have a decrease in the delta L would be lower. That will be negative, right? Okay. And so here we've correlated. This is I put this example up because it correlates the Young's modulus, right, the elastic modulus, to the thermal properties, right? So remember that the strain that you put on by heating something up in thermal expansion, it's still a mechanical strain induced by temperature. So you need to be able to correlate the modulus, the mechanical modulus, to the change in dimensions that occur by changing the temperature. Okay. Okay, so something related to thermal shock. The most important thing here is to know the quench rate. Okay, so if you take something, if you heat it up very rapidly, if you cool it very rapidly, there is a difference in there's a temperature gradient that happens. So if you heat something up to a high temperature, if you cool it down rapidly, it doesn't have time to recover. And if it doesn't have time to recover, or different parts recover in different ways, and that induces stress in the system. Okay, and so the quench rate for fracture is given by this relationship here. Okay, so just know a little bit about those things. So when it comes to thermal properties, those concepts are very important. So let's just go over them again. Okay, so you should know how if I give you say if I give you a material and the material has impurities, right? Or if I give you the electrical properties of the material, you should be able to correlate them to the thermal properties, and vice versa. Okay, succinctly. So based on these 4 parameters here, okay, if I give you again features of a material, if it's a metal, and if it's a metal with small grains, if it's a amorphous metal, if it's a ceramic with large grains or single crystal, if it's a semiconductor with a certain structure, what happens to the thermal characteristic? Okay, so everything's sort of interconnected here, and then this is pretty straightforward. Again, just try to get a grasp of what happens to the material mechanically when you heat it up and cool it down, and how does that happen? And if you do it very fast, what is affected. So you might want to sort of refresh your memory by reading these portions in Callister. Okay. And then, so the light interactions, okay, so light interaction with solids, because this is the crucial thing, right? So, you know, we have photons, right? So we know what photons are, right? Photons are little waves of energy, right? And those waves have both electrical and magnetic components to them, right? So when you shine those waves onto a solid, the magnetic and the electrical components of that wave interacts with the magnetic and electrical components in the solid, the atoms, the electrons, the neutrons, and so forth. And that causes them to, those things in the solid causes the photons to do different types of things, right? So they can be reflected. So the incident photons, which is indicated by I naught here, I sub naught, they can be reflected, they can be absorbed, they can be transmitted, or they can be scattered, right? We discussed different types of scattering mechanisms, right? Elastic and inelastic scattering. You should remember that. What are the conditions that cause the waves to be completely transmitted? Okay. What are the conditions for waves to be completely reflected? Okay. And if I have, if this slab here is a semiconductor, what happens? If the slab is a metal, what happens? If the slab is a insulator, full insulator I should say, what happens? Okay? What, you have three of the same materials down below, okay? One is completely transparent, one is semi-transparent or translucent, and one is opaque. Why does that happen? Okay, that's what you need to know. Okay, you should know what refractive index is, right? That's the sense. Refractive index is just the ratio of the speed of light over the speed of light in some medium. Okay, so light when it interacts with something, it's traveled through a solid. The speed of light is in a medium is lower, right? And the ratio is the refractive index. Okay, so it's important. And so what is I think I've got a slide on that, so let me wait for that. Okay, and then so the crucial thing is why do things appear the way they appear, right? Why is someone's sweatshirt red? Why is it green? Why is it black? Okay, why do so I gave an example of ruby, right? Why ruby is red, right? What are the conditions for colors to be observed? Okay, what gives rise to color? There's a slide in the handout. There's a slide previous to this slide that sort of describes some of those things as well. Okay. So in the case of ruby, ruby is made out of alumina, right? Al2O3. Al2O3 has a band gap of 9 eV. Right? What does that mean? What is that? What should alumina look like?
Black. Reflective.
It's 9 EV.
Black, nothing.
Colorless.
Like colorless, right? It's completely transparent. It should be complete. Something that has a large band gap means that all of the visible photons can go right through it, right? They can go through the band gap. They don't. They have none of the photons excite the electrons from the valence band into the conduction band. The energy is just too high, so none of them get absorbed. Some of them might get scattered slightly, right? But even the scattering cross section is quite low, so it's clear, right? Okay, so you have this alumina that is clear, that has a 9 eV band gap, but in some alumina, like in some sapphire, we know the sapphire can be red, right? We call it ruby, and it can also be blue, right? So what gives rise to these colors? It's dope, right? But what does that mean? It doesn't change the band gap. Yeah. So what do the impurities do? Doping doesn't change the crystal structure. Doping just means that. What is it?
Well, if chromium's got a lower band gap, then it would alter the band gap.
No, the band gap of alumina, remains the same, right? Look what this says. It says it introduces localized levels in the forbidden gap. So you have the valence band and you have the conduction band, and then you have these chromium oxide impurities. Right, the chromium oxide impurities go somewhere, within the band gap. Right, they're like the Fermi level, right, that is placed within the band gap. So you have lots of electrons, right, that are sitting in the band gap from the chromium oxide. The alumina band gaps remains wide, right? It doesn't change. The valence band and conduction band of alumina doesn't change. But when you add impurities, you're doping, right? So if you remember back to your electrical properties lectures, doping is what? What are you doing to the when you dope something? What are you doing to the Fermi level?
Just add free electrons. So you bring it up or down, lower.
Yeah, when what is the Fermi level? What physically is the Fermi level?
It's like your highest, lowest activation energy at room temperature, not room